Hello class, welcome back. Today we're going to go ahead and continue section 2.4, continuity. And in your book, this is going to be page 179. So as we mentioned before, go ahead, right, and read those sections, skim those sections to have an understanding of what the lectures are going to be about, right, what the homework are going to be about. We're going to go ahead and continue with a concept we were introduced in the previous section, correct, where a function is continuous, right? And for a function to be continuous, right, it has to be smooth, right? And it has to, in other words, you have to be able to draw a line without picking it up, right? So every point must be accounted for, right? Every point must be accounted for. Once you put your pen down and you start graphing, you're unable to pick it up. If you were to pick it up and then continue, all right, that is not continuous, right? Right? There's a pothole in the road, right? Something's missing. So we're going to go ahead and expand on that today. In our first example, right, you're given a graph, and it wants you to check which one of the following is true, right? Which one of the following is it true? All right. Well, let's go ahead and find out. Right, for the part A, right? Let's go ahead and number these. Right, we need to go ahead and find out if f of 2 is defined, right? That means if you were to go ahead and plug 2 into the equation, you're going to be given an answer back. I see that if I were to plug in 2, there is a solid circle, right? A solid circle signifies that it is defined, right? So that means that at f of 2, my value is -2. All right, so I agree. It covers that one. I'm told that the limit as x approaches 2 exists, of this given function exists. Well, that's not correct, right? Because I know if I were to take the limit as x approaches 2 from the left, right, it gives me -2. But if I approach the limit as x approaches 2 from the right, that ends up giving me -3, right? So that does not exist, right? I'm told here that the limit as x approaches 2 is the same thing as the function at 2. Well, I already know that's incorrect, right? Because the answer to B, right, it does not exist. It does not exist. It's not the same thing as -2, right? This came from f of 2, right, from part A. So that also fails, right? The function is continuous at x equals 2. Well, that's not possible, right? Because it's not continuous. You're right. It's here, it's here, it's here, and then there's a jump, right? So that is not continuous. The pencil was lifted, right? So it cannot be that. And then I'm told that the function is not continuous at x equals 2. That is true. It's not continuous, right? There's a hole there, right? There's a jump, right? So if I had to choose, these would be, I would choose A and E as my final answer, right? We saw a discontinuity there, right? And there's going to be 3 of them that we're going to be looking at, right? The first one is going to be a removable discontinuity, all right? So you imagine it was a straight line, but then there's a hole there. It was, right? It was removed, all right? And if you see here on this example, right, we see here that it was removed. All right, there's no point there at that A value, right? We have other ones known as jump discontinuities. All right, this is an example. All right, where you have your pencil, you're right drawing, and then you lift it up vertically, and then you continue. All right. And then C, all right, you have infinite discontinuities. For those of you that may remember, all right, what's another name for these? What do you think? Vertical asymptotes, all right, vertical asymptotes. So those are the 3 types, right? And in this section, you're going to go ahead and find these, right, and label them. All right. So for this example, I'm told determine, right, for this, what example? 2.4.5. Determine which of the following rules for continuity is violated first at x equals 2. All right, that it's violated first. All right, so let's see here. Well, it cannot be this one because that's defined, right? It's defined, so I know that cannot be my answer. Well, I know that the limit exists, right? As it approaches from the left and as it approaches from the right, that is 2. Ah, but the bottom one says that the limit as x approaches a is the same thing as the function at a. It's not, right? It's not. So, right, at x equals 2. So that means that the limit as x approaches 2 from both sides, it narrows down on 2, right? And then f at 2, that gives me -2, all right? The solid dot. And, right, these are not equal. Not equal. So that you would choose this one as your answer. All right. I'm asked here to locate the type of discontinuities that I have. All right. All right. So you're going to be giving a graph like this, right? And let's start from left to right. All right. I would say that my f of x function has a discontinuity at has a, well, first let's label. There we go. What type of discontinuity, right? Let's go ahead and locate this one. What type of discontinuity, right? Which one of the threes would you think that one is? Yes, if you said removed discontinuity at x equals -5, you're correct. All right. Let's go ahead and let's go ahead and move on to this side. All right, I would say f of x has a, what type of discontinuity? A jump discontinuity, right? At what x value? At x equals -2. And last but not least, right, it's going to be, right, that one there. X has an infinite discontinuity at x equals, what is that, 7. All right. So those are, right, it's going to be our job to go ahead and locate those. All right. So I want to go ahead, right, start splicing things together. All right. Domains, right? Your domains function. This ties in with determining if a function is continuous or not. Right? If it's a function is continuous or not. Whenever we're dealing with rational equations, right? Let's just say here, right, for problem A, you can find the domain of the function, right? You can go ahead and find the domain of the function by getting the denominator and stating does not equal 0, right? Why? Because we cannot divide by negative value, right? It gives me, it's undefined. All right. You go ahead and solve this, and hey, you find out that your x cannot be -3. It's able to be anything it wants, except that. All right. So your domain in interval notation, all right, would be from negative, right? So as a refresher, right, you may want to go ahead and draw the number line. All right. All right. So you cannot be that, but you can give me anything to the left of that or to the right of that. Right. So this means that this domain in interval notation, right, this would be from -infinity to -3 union, right? It's, in other words, it comes, you read these from left to right, right? You get closer here, you do a little jump. That's going to be my union. And then from -3 all the way to positive infinity. All the way to positive infinity. All right, so in other words, this function, in other words, its domain is from negative infinity to 3 union from negative 3 to infinity. Or another way you can say this is the domain in which this function is continuous is that domain, right? It's continuous everywhere on that domain. Let's go ahead and do another one. All right, so you have a square root function. All right, so since we're dealing with just with calculus, right? This isn't complex analysis, right? We're not dealing with complex numbers. The only real values, all right? We know that with these square roots, we can take the square roots of 0 and anything positive. It's the negative when the problem arises, right? So since I'm able to take the square root of a negative value, right? Since you're able to take the square root of a negative value, you would state that this here, you would get everything inside your square root and state everything on the inside must be greater than or equal to 0. All right, you would then go ahead and solve for your variable. Right, and if you remember, whenever we're dividing by, when you, the mathematician, is dividing by a negative value, your inequality flips, right? So then this is x is less than or equal to 6. All right, so in the number line, right, you would have something like 0, 6. You can include 6, right, because it's less than or equal to, and the arrow, right, it's pointing to that way, to the left. Or in other words, you want everything less than 6, right? So this function is continuous everywhere from negative infinity all the way to positive 6, right, with 6 being a bracket. Right. With the logarithmic functions, right, with logarithmic functions, the log at x equals 0 is, right, so if I'm looking at just the parent function, it's not defined at x equals 0. Right, it strictly must be greater than 0, not greater than or equal to 0, but strictly greater than 0. So you would get everything inside your log and just state it has to be greater than 0. All right, and you would go ahead and then solve, right? Go ahead and solve. Right, so this here would state, right, for regular logarithms with parentheses, that your function is continuous, right, as long as it is greater than -2, right? So again, in a number line, right, it's going to be an open circle, all right, and you want everything greater than that, right? So it's going to be all the way to the right, right? So the domain that would make this function continuous is from -2 all the way to positive infinity. Very nice. Okay. For our natural log functions, right, which are, they have the same properties as the the logarithmic functions, but specifically here you're dealing with the absolute value, all right? The natural log of everything on the inside is the absolute value, all right? It would be here that you get everything on the inside, and you strictly say this cannot be 0, right? It cannot be 0, and then you would go ahead and solve for your x, right? Sorry. Cannot equal 4, but it can be anything else, right? It can be anything else. All right, so it cannot be 4, right? So I would exclude that, but it can be everything to the left. It can be everything to the right. All right, so the domain of this function where it is continuous, it is from negative infinity to 4, a little hop, union, or to infinity. Right, and last but not least, right, are your polynomial functions, right? There's no inequalities, right? There's no inequalities. There's no There's no rational equations, all right? It's not a fraction. It's just a regular polynomial, all right? Regular polynomial. Well, the domain for this is all real numbers, right? So in other words, from negative infinity to infinity, this function is differentiable. It is continuous on all real numbers. All right. We mentioned earlier that with piecewise functions, all right? We mentioned that with piecewise function, things are happening to the left and things are happening to the right. All right. So to the right of this, right, I have to the left of it, I have this equation that's mx minus 15, all right, where m can really be any number. And then I have to the right of that asymptote, right, to the right of this line here, this vertical line here, another function exists, right, which is x squared plus 5x minus 8. All right. And right, we said, right, that if the right one looks like this, the left one, if it has a variable, it can do something like this. It can look something like this. Right, that it all depends with that m or that c, right? I think for the last example we had a c. All right, it can be anywhere, but you want it to be aligned on top of that one. All right, and the reason you want it to be aligned on top of that one, it's because if its endpoint is here and the graph looks something like this, at that point you splice two things together and it is continuous. All right, and how do you do that? Right, if you want two lines to go ahead and meet each other, we said we're going to go ahead and equal these to one another. Right, I'm going to get the top and I'm going to equal it to the bottom. All right, and you're going to solve for the m or for the c, right? You'll see the capital A and a capital B and a capital C a lot, right? But it's the same process, right? You equal it to one another, and you may be asking, hey, do I solve for x or do I solve for m? You're going to solve for the other letter, because where do you want these two lines to meet? At x equals what? At x equals -7. All right, so that means you're going to plug in -7 for every x that you see. Right, so this gives me -7m minus 15 equals 49 minus 35 minus 8. Go ahead and plug this in. Right, this here on the right hand side, right, this gives me 6. All right, I'm going to go ahead and add 15 to both sides. Right, so this gives me -7m is equal to 21. Right, and last but not least, I'm going to go ahead and divide by -7. So m is equal to 21 divided by -7. So m is equal to -3. That means in order for this function to be continuous everywhere, right, at x equals 7, right, so for them to be spliced there, right, that m must be -3. And when it is -3, this entire function would be continuous. Okay, and here's a true or false one. I'm told that my f of x function is continuous at x equals -9. All right, so I'm told, right, and you can go ahead and make an example, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's 9, that's 8, that's 10, right? I'm going to say that it is continuous at 9, okay? And 1, 2, 3, 4, 5, 6, 1, 2, 3, 4. Right, and I'm told that whenever x equals -9, oh, it's the other way, I'm sorry. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all right? Whenever x equals -9, right, the y that's associated with that is -6. So that means this point exists. And since that point is continuous, I know there's something probably going on to the left, and there's something probably going on to the right, right? Because it's continuous, right? It's continuous at that point, right? So, and then I'm told, hey, is it true that the limit as x approaches -9, it's -6? Hey, yeah, that's true, right? Because my function is continuous at x equals 9, x equals -9, and I know that at that point, my f at -9, it equals -6. Since it was continuous, it must be that, right? For this example, limit as x approaches -9 of this function must equal the function at that point, right? So yes, here would be true. Okay. Going to go ahead and continue on to section 2.5. All right. So as you might have noticed, I'm not going to go ahead and cover everything. This is why I've gone ahead and linked the video examples for you to watch at your own pace, all right? But if there's anything you may need a further explanation, or if it's something that I wish I had given you personally, or I gone ahead and give a better explanation, that's why I'm making these videos, all right? I'm making these videos. So, right, we have here the precise definition of a limit, right? There we go. There we go. This is going to be section 2.5. Yes, the precise definition of a limit, all right? Right, let f be a function defined on some open interval, right? So it means it is continuous from the left and it goes on to an interval to the right that it's continuous, right? Kind of like here. It starts here and it ends there. All right, that is my interval between there and there. All right, you can say between A and B. All right. And we see here that as x approaches A, all right, because we're still dealing with limits here, the answer that's produced is L, all right? You know, that just means that whenever your function, right, your limit approaches A from both sides, the answer that's spat out, right, is L. And if I notice here, right, there's this distance that exists here between that A function, right, which you can associate with X, right? There's a distance here. All right, and that distance on the vertical axis is your delta, right? Your delta, and all that means is that if you were to find a point here and go all the way up, it's going to bounce and reflect, right? And it's going to create a new distance, right? It's still going to go ahead and create a distance, but it's going to create a distance between the answer, right, on the vertical axis. And this distance, right, that's known as an epsilon, right? That distance up there is known as an epsilon, right? Right, and right, this distance here, right? And you can go ahead and go backwards as well, right? So you wanted to find that same distance, but from the left of A, right? So then the left of A, all right? So that's the same thing, right? You would go up, right? You would go ahead and go up. This line should be here, right? This means if you were to go ahead and go up, it'll reflect and hit somewhere here, right? It will hit somewhere there. All right. So that's where exactly we're going to find. We're going to go ahead and find those distances, right? We're going to go ahead and find those distances. Oops. Right, we're going to go ahead and find those distances by using this definition. All right. So the limit as x approaches A of a function is equal to L, right? Whatever the answer ends up being. All right. And for every number epsilon greater than 0, there exists a number delta such that, and this here is what we would have to memorize, all right? We're going to go ahead and learn how to use this, all right? Specifically, I want us to remember these, what I'm highlighting here in yellow. All right, what I'm highlighting here in yellow. All right, so let's go ahead and apply this, all right? And I'm going to go ahead and apply this, all right? And remember, at the end of the day, these math problems are just puzzles, right? And we're going to learn how to use these puzzles, all right? So I'm told here, all right, I'm going to go ahead and apply the precise definition of a limit to find my delta and my epsilon, okay? My delta and my epsilon. I'm not going to go ahead and read this question just yet, all right? I want us to understand how to use this first, right? So I'm told that the limit as x approaches -1 of 3x plus 3 is equal to 0. And you can test this out, right? You would go ahead and plug a -1 into there. You'd find out that it ends up, it ends up giving me that, right? It ends up giving me that. So what I'm going to go ahead and do now, all right, is this here is exactly, right, the limit approaches a of a function L. All right. So in other words, a is this -1. My function is this here. And my L is the answer. All right. And all I'm going to go ahead and do is plug that into my definition, right? So in other words, I'm told if 0 is less than x minus a less than delta, then, let's go ahead and make this a little bit bigger. Then the absolute value of my function is less than L, is less than, minus L is less than epsilon, all right? I'm going to go ahead and plug in what I know, all right? First, I'm going to go ahead and plug in what I know. I know if 0 is less than x minus, what is my a? -1 is less than delta. Then my function, right? What is my function? My function is 3x plus 3 minus L. What is my limit? All right, my limit is 0. It's less than epsilon. All right. What I'm going to go ahead and do here, just polish things up just one more time, right? So in other words, simplify. All right, so this is going to be x plus 1 less than delta. Then plus 3 is less than epsilon. All right, so that's what I have. All right, the point of the game here, right? Your goal here is to make your epsilon part here, all right, look just like this. All right, you want everything inside the square root to look like, you want everything inside the absolute value to look like that. So in other words, that f of x minus L part, you're gonna have to factor things out. All right, for all of these, you're gonna have to factor things out. So one thing that I know I can factor out is a 3, right? I can factor in a 3 from there, right? And I know, right, that whenever I have the product, right, whenever two things are multiplied inside an absolute value, you can apply it to each one individually. And I know what the absolute value of 3 is, right? What is the absolute value of 3? That is just positive 3, right? It remains positive. And last but not least, I don't want, right? I don't want that. I do not want the 3 there, right? Because this one, it doesn't have anything in front of it. All right. So in other words, I'm going to divide both sides by 3. So in other words, the absolute value of x plus 1 is less than epsilon over 3. All right. And if I hadn't given you a delta or an epsilon, all right, at this point, once these two are matching, all right, once these two are matching, you can state delta is then equal to epsilon over 3. All right. Delta is then equal to epsilon over 3. If I gave you an epsilon, right, you would plug it in. If I gave you a delta, you would plug it in, right? So another answer you can choose here where you're solving for epsilon, right? If you were to multiply both sides by 3, right? So 3 delta is equal to epsilon. All right. 3 delta is equal to epsilon. So for this example, all right, example that was here that was given, I did give an epsilon, right? 0.1. All right, so I'm going to go ahead and do that. I'm going to go ahead and continue here a little bit further. All right, so delta is equal to 0.1 divided by 3. All right, let's find out what that gives me. All right, this states here that this is 0.0 with repeating 3s. All right, we'll go ahead and do that many sig figs. All right, we'll go ahead and do that many sig figs. All right. So, all right. So that would have been my answer, right? That would have gone ahead and been my answer. But All right. Your options are going to be more than that, right? You're gonna have various options. All right. So what I have here, right? What I have here, right, is since now I know what epsilon over 3 was, right? Epsilon over 3, right, is this is just x plus 1 is less than, well, epsilon over 3 was 0.1 over 3, or this here is just 0.0333. All right, 0.333. But right, if that is my delta, all right, if you solve for your delta, right, let's go ahead and break this down here, right? This is just 0 is less than the absolute value of x plus 1, right, which is less than delta, but you already know what delta is. Your delta was, let me go ahead and scoot this a little bit over. Right, your delta was 0.0333. Right, so it's safe to say then, right? It is then safe to say, right? Because if delta is greater than this, right, and this is greater than 0, right, you can say that 0 is less than delta is less than or equal to this value, right? So that is true as long as your deltas exist there, right? As long as your deltas exist there. So in other words, if I had given you an option, right, with, hey, which one of these delta values suffice, all right? So let's just say here I had given you 0.123, 0.0022, 0. We'll do 1, that's a 2 over there, and negative 0.23. All right. These are your options, right? Which deltas would you choose? Well, I know that the deltas I can choose have to be strictly greater than 0, but less than 0.03. All right. This here is too big, so that's a no. This here is smaller, so that's a yes. All right. This here is too big. All right. So that's a no. And this here is negative. That's definitely a no. All right. So that means the answer you would have chosen would have been B. All right. Let's go ahead and do another example. All right. We're going to go ahead and apply the same thing. All right. We're going to go ahead and apply the same thing. And here I've given us some few options. All right. I've given us some few options. So the first thing I'm going to go ahead and do, right, is going to go ahead and I'm going to write out this limit as x approaches -1 with my function being 5x plus 3 is equal to -2. All right. I know that this is the limit as x approaches a of a function is equal to the limit. All right. And following the precise definition of the limit, all right, I know that this is if this then that. Right? And we said we were going to go ahead and locate my alpha, my A, which is -1. My function, which is 5x plus 3, and the limit, right, which is -2. And I'm going to go ahead and plug that in. Right? I'm going to go ahead and plug that in. So this means if 0 is less than x minus -1, less than delta, then that function 5x plus 3 minus the limit, what my limit being -2 is less than epsilon, right? So we said we're going to go ahead and polish things up, right? We're going to go ahead and pretty much simplify. So this is x plus 1 less than delta, and 5x was that 3 plus 2, that's going to be 5. Right, and we said that we're trying to factor things out on the right such that they end up looking just like this. All right. So in other words, the one I'm going to manipulate is going to be the one on the right. I'm going to factor out a 5. All right. This, and I know the absolute value of 5. That is just 5. right? And then I divide both sides by 5, right? So I'm told here that the x plus 1 is less than epsilon over 5, right? Meaning delta is equal to epsilon over 5, all right? But hey, right, if I write in the exam, if I don't give you a delta and epsilon, this is it, right? You would just need to create a relationship. You can either leave it like this, or you can say epsilon is equal to 5 delta, all right? And all you have to do there, right? How did I get that? Multiply both sides by 5, right? Multiply both sides by 5, all right? But here, I do give you an epsilon, right? I go ahead and say that epsilon is 0.4, so I can't continue, right? This is 0.4 divided by 5. Right, let's go ahead and plug that in. 0.4 divided by 5. This gives me 2 over 25, which is, oh, give me 1 second. 0.4 divided by 5. Why did I say 25? This is 0.08. Right. Since delta is equal to epsilon over 5, then that means the right hand side is just 0.08. Right, when I bring this down, I know this is 0 is less than x plus 1 less than delta, which is 0.08. All right. But if delta is greater than this and this is greater than 0, then you can say that 0 is less than delta, which is less than or equal to 0.08. All right. But here you have some options, all right? You do have some options, all right? 0.02 with ongoing sixes. That is less than 0.8, right? So I can use this. I would say yes, I can use that. The right-hand side is I can't, right? It's an equal sign, right? It's less than or equal to 0.08. So yes, I can use that. All right. This here is larger than 0.0064. I can use that. All right, but 0.16, it's too large. It goes out of bounds. So, all right, so that one cannot be included, meaning I only have three possible solutions, right? That suffice those delta values. So very, very nice, very, very nice. We're gonna go ahead and now jump to section 3.1. Right, and in the previous sections, right, we went ahead and spoke about using the definition of the derivative, right? The difference quotient, right? F of x plus h minus f of x all over h. And we're going to be doing the same thing here again, all right? So we're going to be applying to the same thing here. Applying the definition of the derivative, right? As the limit as x approaches 0 of the, right? So in other words, I want you to go ahead using the definition of the derivative to derive this function, which is 5 over x. All right, so I know that my function is 5 over x. All right, so this means that f of x plus h, all right, we said that all you're really doing is replacing x with x plus h. So in other words, this is just 5 over x plus h. Let me go ahead and make this bigger for you. X plus h, right? And at this point, I really have everything that I need, right? There's no square roots. There's no spoiling method. You are going to have some foiling method once for your homework, right? But for this one, there isn't, right? For this example here, there isn't. So let's go ahead and plug everything in, right? So the limit as h approaches 0 of f of x plus h, that is just f of x plus h minus f of x. F of x was just 5 over x all over h. Right? It's so whenever you have these rational ones, right? Try not to let it intimidate you, right? It's a step at a time, right? Just take it a step at a time. I'm not going to worry about this bottom h part. I'm not going to worry about the bottom h part. My numerator is always my focus, right? So I'm going to go ahead and focus on that numerator. I have two rationals, right? I have two fractions. And I know in order to add a fraction or subtract a fraction, they have to have what? They have to have the same common denominator. All right. So when I'm comparing these two, right, what would be my lowest common denominator? All right, so to find it, right, one way you can find it is everything in the denominator you're going to treat as one piece, right? And I'm going to go to each denominator and I'm going to write down what I have, okay? If it repeats, I'm not going to write it down again. If it's new, I'm just going to multiply to what I already had in my LCD. So in other words, one of the ones I have is x plus h, right? And you're going to treat that as 1 unit. Right? You're going to go ahead and treat that as 1 unit. Right? I'm going to move on to the next denominator, which is x. Right? X, remember, x is very different than x plus h. All right? So I'm going to go ahead and multiply it there. But right, we generally like the x's, right? That looks fine, right? You can either have it like this, or if you wrote it down like this, right, how we're used to seeing it, it's the same thing, right? So the game here is, now I'm going to go to my first fraction, the one here, and I'm going to find out, does the denominator here look like my LCD? No, it doesn't. What is it missing? An x, all right? So in other words, I'm going to multiply this by an x and the top as well, right? We need to keep things balanced. Whatever you do to the bottom, you do to the top. And I'm going to go ahead and go on over to the next one. What is it missing? It's missing an x plus h. So I'm going to multiply that to the bottom and to the top. Right? Bottom to the top. Meaning that now I have the limit as h approaches 0 of 5x over x times x plus h minus 5x plus h over x times x plus h. All right. I know that once you have the same denominator, all right, you can combine things and the denominator stays the same. So I have the limit as h approaches 0 of 5x minus 5 times x plus h over x times x plus h. Oh, right, and I'm sorry. Sidetrack. I know everything for me is all over h, right? Right, all over h, right? Let me go ahead and keep focusing on that numerator, right? So what I'm going to go ahead and do, right? I'm not going to be focused on that denominator, all right? You want to leave those denominators as is, all right? You don't want to really distribute into there, right? You want to just leave it like that. It's nice and compact, right? We like that. What I'm going to go ahead and do is just distribute this negative into there, all right? So this is going to be 5x minus 5x minus 5h all over x times x plus h all over h, right? And this is the limit as h approaches 0. All right, we see that those 5x minus 5x, that cancels out, right? So I'm left with the limit as h approaches 0 of negative 5h all over x times x plus h all over h, right? And when you have a fraction on top, right, this is my top part, divided by something else, all right, I don't want this one here, right? I don't want that one here. So what I'm going to go ahead and do is multiply by its reciprocal, which is by times multiplied by 1 over h, so I can get rid of it. And I know whatever I do to the bottom, I need to do to the top, right? So the bottom just cancels out, right, leaving me with the limit as h approaches 0 of negative 5h over x times x plus h times 1 over h, all right? This here is just the limits as h approaches 0 of negative 5h over, you can say, h times x plus h. Hey, what happens with the h I have on top and with the bottom? They cancel out. And that's great, right? Remember, whenever we were doing these, we say we like it when they cancel out, right? That's a good sign, right? So this means I have now the limit as h approaches 0 of negative 5 over x times x plus h, right? What I'm going to go ahead and do now, right now that I cancel out, is we say we're going to go ahead and take the limit, right? So that means wherever I have an h, I'm going to put a 5, I mean a 5, what am I saying? A 0, right? So this is negative 5 over x times x plus 0, right? X plus 0, that's just x times x, which is what? Negative 5 over x squared. Hey, and that's it. That's it. This would be my answer, right? Right, that would have been my answer. If for some, right, if I had asked you, I want you to do all this, right, to define the derivative using the limits, right, and at the end I say for or at x equals 3, that means you're going to do the same process, right? You're going to go ahead and do all the way. You're going to take your limit, and it's going to give you this. And once you get here, for every x that you have now, you're going to plug in a 3. So if I would have asked you, hey, I want you to define the derivative of the function 5 over x for x equals 3, right? You would do, right, we would do the same thing. Nothing changes. We're going to go ahead and get this new function, right, the derivative, and then I would go ahead and plug in a 3 and simplify. And I should get a numerical value, right? So that answer there, the derivative of that function at x equals 3 would have been negative 5 over 9. Okay, negative 5 over 9. There were a few things I wanted to go ahead and cover whenever we're talking about the derivatives, right? Especially whenever physics problems start coming up. I need us to remember that, and right, this is going to be very important to write down, right? You're going to get some physics problems where you're giving position, all right? And you can go from position to velocity by taking the derivative, all right? If you have a function that is position, if you were to derive that function, it'll give you velocity. If you have that velocity and you were to derive that again, this here would give you acceleration. Very, very important that we remember this, all right? So in other words, if you start at position and you derive it once, it gives you velocity, right? If you have position and you derive it twice, 1, 2, it's going to give you acceleration, right? Another thing to remember too is if you start with velocity and you derive it once, it gives acceleration. Okay, it gives us acceleration. We can work backwards, but we're gonna, right, we won't see it until towards the end of the semester, right? We can work backwards, all right? And we'll see that much later, right? So remember that. Oh, and just one more thing too. If you have velocity and you want to know speed, right? Speed is just the absolute value of velocity. That's all it is. So if for some reason they were to say, hey, your velocity is -5 meters per second, then your speed is just the absolute value of that number, meaning if it's negative, if it's positive, and if it's positive, it's positive, meaning your speed would just be 5 meters per second. Right. Another thing I want to go ahead and mention is whenever you have a function, right, specifically this is known as an execute function, all right, and it'd be very important to get familiarized again with our parent functions, all right? So we're not really familiar with the absolute value of x cubed, x squared, the square root of x, a constant. I would look those up, all right? They're going to be very, very handy in these upcoming sections, all right? So you just, I don't want us to memorize. I want us to just know them, all right? So whenever you're studying, don't see them as memorizing. You just know them, all right? Just like whenever you're driving, right? You don't memorize how to drive. You just, after a while, right? You just know how to drive, all right? You don't have to think. It's just subconsciously there. So one thing I wanted to mention is this is a positive execute function. If you were to derive that, right, it'll give you an x squared function, a positive squared function. And a positive x squared function looks like this. If you were to derive a squared function, it's going to give you a line with a positive slope that looks like that. All right. If you were to derive that positive, right, that function, it'll give you a constant, but a positive constant, right? Meaning a constant is just going to be a horizontal line, right? So in other words, it'll be somewhere like there, right? Or somewhere here, or even somewhere here, just something above the y-axis, right? And if you were to derive a constant, this is 0. right? If you're dealing with a negative x cubed function, right, that looks like this, right? If you were to derive that, it's going to be a negative x squared type of function, right? Which we know if it's parabolic up, it's going to be parabolic down. If you were to derive that, it'll give you a linear function with a negative slope, which goes downwards, right? And if you derive that, it'll give you a negative constant, right? That just means that horizontal line is now going to be in the y-axis. It can be there, it can be there. It just has to be wherever y is less than 0, right? And if of course, if you were to derive that, it'll give you 0 if you derive a constant. So this is very important, all right? I'm going to put a big star on this, all right? I'm going to be referring to this, all right? Because things like this, knowing these things like that, it's going to be very useful whenever you're doing process of elimination, right? So, right, what are derivatives, right? A derivative is just a slope, right? One thing I wanted to mention earlier, and I apologize for it being late, is really all you're really doing in this class is finding slope of functions, right? That's all we're, for the most part, what we're doing, right? Finding slopes for x equals a number or x doesn't equal a number. So for some reason, if I had asked you, hey, look at this function here, right? It has a few curves. If I were to say, hey, give me the slope at here, right? It's just a straight line that looks something probably like that, right? And as you start curving down, right? As you start curving down, that slope changes, right? Now it's doing something like that. As you get closer to something like it, starts getting something like that, right? And as you keep moving to the right, you're gonna hit a point where it's horizontal. And then as you keep going to the right, it starts picking up. Right? It starts picking up. All right, and at this point, it's very, very, very almost high, right? But as it gets closer to that other max point, right, to that hill, it starts flattening out again. All right, and that's oops, no, that's really, really all it's doing, right? You have horizontal tangents, right? In other words, you have horizontal slopes, right? Horizontal tangents are your horizontal slopes whenever you have max and minimums of smooth curves, right? So we know that our curves have to be smooth and continuous, right? For it to be differentiable, right? Hopefully we've already read that part of the book, all right? Like I said, we need to go ahead and skim the book to get, to get that, all right? And so the horizontal tangent is going to be my horizontal slope. And one thing to remember is you're going to have horizontal slopes wherever you have max or mins, right? So you have one there, you have one there, you have another one here, and you have another one here. All right. So if I were to ask you, hey, all right, if I were to ask you something like, what can I ask you? Give me the x values in which this function here that I drew for you has a horizontal slope. That'll be at, let's see, that's 1, 2, 3. That'll be at x equals -3. There's another one here, right, at x equals 2. We'll say this one is 3, 4, 5, 6. We'll say that's 6, right? That is at x equals 6, and 6, 7, 8, 9, 10, right? At x equals 10. Right, so at those specific x values, the slope is 0, right? Or your horizontal tangent, you have horizontal tangents, meaning that it's a horizontal line, right? That your slope is 0, right? Slope is 0, right? It's just 0. All right. In order for your graph to be differentiable, it must be smooth, right? Smooth is something wavy, like a wave, right? Very serene, right? Very, very smooth, right? It's smooth. And it must be continuous, right? Meaning that there cannot be open dots, right? There can be no jumps or infinite discontinuities, right? And what, right? So one thing you may be asking, hey, I already know what continuous is, right? How do I know if something is not smooth? Right? Something is not smooth if it takes a sharp turn. That point right there, that is not smooth. I tell you that, right? That is not smooth at that point. That made a sharp turn. That means your function is not differentiable there, right? So let's just say I had drawn something like right, and let's just say I did something like that, right? And I want you to tell me at which points in this graph is a function not differentiable. In other words, look where it's not smooth and look where it's not continuous. Right here, it made a sharp turn at x equals -3. So I would say at x equals -3, not differentiable because not smooth. Right, and then we see here that at x equals 2, that it's not differentiable because not continuous, right? So again, it all comes back down to the definitions, right? Knowing these definitions, right? And again, like I wrote it down there, right? Your points must be smooth and continuous, no sharp turns and no discontinuities, right? So again, right, this is what we've covered, 2.4, 2.5, and 3.1 for homework module B, I believe. If you have any questions, don't hesitate to send me an email, and happy studying. Thank you for your time.